I have a patient, her name, let's call her Anne. She works at a big tech company near Stanford where I run my lab. And usually, Anne is a bundle of energy, working 12-hour shifts as a software engineer, rock climbing for fun, always telling me where I should go on my next vacation, including here in Napa. But a few times each year, Anne gets depressed. And when she's depressed, it takes all her energy just to get up out of bed and put her clothes on. The effort just seems too much to bear. Anne calls this climbing into my pit, and none of the available treatments help her climb out again. All we can do is wait. The goal of my lab, the STAR Lab at Stanford, is to figure out how this happens and what we can do about it. I use mice because, believe it or not, in the right context, mice can act a little bit like they're depressed, and all without a tiny little couch for them to lie on and tell me their problems. The amazing thing about mice is that we can use all the latest tools in neuroscience to peer directly into their brains and get a sense of what's going on in enough detail that I think we can actually make new, more effective and more targeted treatments for patients like Anne. So I'm going to give you a tour of some of what's going on in my lab right now and how I think this is going to translate up soon. Last year, I published a paper looking at how the brain encodes effort. And for this paper, I trained mice like this one to poke its nose in a little hole to get access to a drop of juice. Sometimes it was really easy. They had to poke their nose once and they would get the drop of juice that they really wanted. But sometimes it was hard. They had to poke 50 times in a row just to get a single drop of juice. And all the while, we were using powerful new sensors to record the ups and downs of dopamine in their brains while the mice were performing this task. You've probably all heard of dopamine. It's a chemical in the brain that's been linked to rewards for more than 50 years. But surprisingly, before this paper, very little was known about what happens to dopamine when you keep the reward the same, but you change how much effort it takes to get that reward. What we found is that the very same reward evoked a huge amount of dopamine, a lot more, when the animal had to work hard for that reward. When I saw this graph for the first time, my jaw dropped because it's one of the first demonstrations in the brain of a psychological concept that I think we all know something about, the sunk cost effect. The idea that we value things more when we've worked harder for them. So like in this cartoon, the sunk cost effect can get us into trouble sometimes, make us hold on to things for way longer than we otherwise need to. But it turns out that almost every animal does this. Pigeons do it. Ants even do it, starling birds, and of course there are many examples in people. One of my favorite examples is the so-called IKEA effect, in which people will actually value the same piece of furniture a lot more if they laboriously built it themselves compared to if they bought it pre-assembled. Okay, so this exists everywhere we look, and yet it can get us into trouble. So why did evolution conserve this? I think it's because it's evolution's way of motivating us to keep going when things are hard. By assigning more value to things that we work hard for, it reinforces the effort that we put in and lets us keep going. So dopamine does something with effort encoding, but how? How does dopamine know how much effort we've put in? It's another neurotransmitter that does the magic. After looking at every possibility we could think of, we discovered that it was acetylcholine. When a reward is hard-earned, it evokes a huge burst of acetylcholine release, which then triggers dopamine. And if you block this interaction between acetylcholine and dopamine, you impair the animal's motivation. So when a reward is really easy to get, blocking this interaction does nothing to the behavior. The animals earn just as many rewards as usual. But when you make it hard to get those rewards, now blocking this interaction impairs their motivation. The mice give up. They act almost like Anne or other patients in the midst of a depressive episode when the effort feels too much to bear. When I found out that I was one of the awardees this year of the Rising Star Award, I was so excited because I knew exactly what I wanted to do with the funding. I wanted to figure out what happens to this circuit in the midst of a depressive episode. I'm going to record this circuit in mice experiencing chronic stress and all of the motivated impairments that come along with it. And then I'm going to use a combination of pharmacology and brain stimulation to try to restore normal activity in this circuit and then rescue normal levels of motivated behavior. And once I do this, I'm going to try to take it to human. And that's going to involve collaborating with lots of other scientists who study depression, with companies who are interested in this space, and it's likely going to involve lots of iterations of approaches. So maybe neurofeedback, like my fellow awardee Laura is going to talk about. Maybe deep brain stimulation, like my fellow awardee Moses is going to tell you about. Or maybe pharmacology, those beautiful interactions between drugs and their receptors that Ed and Annegret are both working on. Or maybe all of the above. I'm convinced that we'll find an approach that works because I believe in a future in which patients like Anne never have to climb into her pit ever again.